Okay, dear students. So in previous lectures, we have read about the fundamentals of semiconductor physics. Then there are three types of materials: your conductors, your insulators, your semiconductors, and having possessing different properties. And after that lecture, we have studied about the pure and impure semiconductors. Pure semiconductors, that is known as intrinsic semiconductor, and impure, that is the intrinsic semiconductor with dopants. And by making use of dopants, you can create two types of semiconductor. That is, one is your N-type semiconductor. N stands for electronic charge, having majority charge carriers are electrons, and p type stands for positive charge, positive charge carriers, and in semiconductor those are holes. And we have studied in detail all about these basic fundamentals. In the next step, we have created the p-n junction by sandwiching the p-type semiconductor to n-type semiconductor. Okay, let's recapitulate that. That's very important for the today's topic, because we have to move one step ahead, that we want to create the ordinary PN junction in forward wise mode and in reverse wise mode. Okay, so let you see on my board that when we have a p-type and n-type junctions, we have already created that in the last lecture. Let's recapitulate. We have I know this is a p-n junction. p-n junction, what you have done, you just take a p-type semiconductor and then n-type semiconductor, because individually they have no importance, they have no importance. So what you do, you just sandwich the two. Like, we have different techniques for doing that. It's not very easily. These are some special techniques that we have to sandwich the two types of the semiconductor. There is a, yes, I think I have mentioned in my previous lecture those techniques in brief. Yes, there is a first technique is ground junction technique. Second technique is fused or alloy junction, and third one is diffused junction method. These are the special techniques how you can fabricate the PN junction diode in practical way. It's not just like you just cement the two, because that will create the discontinuity, and it's not the size, because you are dealing at very small size of the atoms, atomic levels there. So that will definitely create the discontinuity. So these are the few techniques, important special techniques that used to fabricate the PN junction. Okay. So after that fabricating the PN junction, then there is a small physics that comes into our mind, that if it is a p type, this is the p type section, p region in this side, and the second n region is this side. For example, you can take npp, and it's up to you, it's not very big deal. So okay, then yes, what we know that in p side your majority carriers are positively charged particle, and these are holes. Positively charged particles are the majority carriers, and these we know that we know all these things. And from for n side, majority carriers are your electrons, are their electrons. Okay, or in the physics point of view, I can say that this is the high concentration region of electron, that is n side, n section and region, and there is a high concentration of holes in the p region. Okay, and we also know that it's a natural way that if you want to take the charges from one point to another, then there is a positive region to negative region, यानी we can say that हाई कंसंट्रेशन से आप लो कंसंट्रेशन की तरफ ही किसी भी फिजिकल क्वांटिटीज को ले जाते हैं, और इट्स अ नेचुरल लॉ. So if I make if I draw these majority carriers, so I have in this section, I am considering, yes, there are holes are the majority carriers in the p section. I am making this, right? Okay, then these holes are also bonded to the lattice. Which lattice? Lattice of silicon. Lattice किसका है आपके पास? It is of silicon. If these are holes are positive charge, then this is negative. These are bonded like this. These are bonded like this. This is the bond between the lattice and the free charge carrier, whatever it be. So yes, this is. So I can represent the actual scenario there. There is we can represent, yes, and in another sense you can think that these are the ions of the dopant. If it is p type, we know that it is p type, then there is addition of trivalent impurity. Trivalent impurity is there. Trivalent impurities, for example, you have indium is there, you have aluminum is there, you have gallium is there, having Z, that is 31, you know this. Okay, so the scenario is like these. I can represent these impurity ions that is in contact with your majority charge carrier of your p section, right? In analogous to this, if I want to see the electrons on the second side, then there is majority carriers of electrons are like this. These are the electrons, majority carriers in your n section. There are majority carriers like this. But here, this region is n region, that is having the pentavalent impurity, for example your arsenite, phosphorus, antimony, Sb. These are the dopant that are doped in this section of the semiconductor to make it n region, to make it n type of semiconductor, that is extrinsic one. Okay, so if this is the case, then these free electrons, they are also in contact with pentavalent, that is dopant. If this is negatively, this is the negatively charged, then this is your positively charged, like this. The situation is this. Actual situation is this. So these all electrons are in contact with your dopant ions on both sides also. Like this. This is your first step to understand. To understand, right? What happened? What happened? I know that. I know that there is a flow of any quantity, any physical quantity from high to low concentration. This is the natural law. High to low concentration, there is a flow of, it may be your electrons, it may be your holes, that is the positively charged, like this. I am writing that this is maybe H, hole. H is positively charged. Okay? So what happened? Now what happened? Now the scenario will change. What happened? In the very first step, in the beginning of the, you just fabricate the PN junction diode. This is very instantaneously the process takes place. Okay? So your holes high, yes. One more thing is there. Along with the majority carrier, there is also the minority carriers. There is also existence of the minority carriers. In N side, the minorities are your holes, and in your the second section, I want to give the color. So there are holes. Yes, holes should be the minority. Sorry, electrons should be the minority carriers there, like this. This is the actual vision, actual and ideal vision, not actually. This is the ideal vision how we can think for PN junction diode. Right? Now there is there is movement of charge carriers takes place. So high concentration electron start moving to low concentration region. Electrons path would be like this. Electrons start crossing this junction towards the, that is from N to P region, and in similar way your holes, they start to move from P to N, because in P they have high concentration, and they start to do like this. They start to cross the junction due to variation in the concentration of the charge carriers, right? So in this we can think that this process start instantaneously when you just do this. Now what happened? What happened? If this is the case, if this is the situation, then now see the whole PN junction, that yes, if okay, if I have this hole and let this free electron, because this is negatively charged, this is your positively charged, what happened? They start combining positive and negative. They start combining. When they combine, I'm saying it recombination. I say this process recombination takes place, because positive, negative, neutral. Then this is the situation for recombination. So there is a recombination starts. If there is a recombination start, yes, from this section this electron move to this hole for recombination, but in actual way, that is also attached to this dopant ion is there, and this dopant ion is there. This is negatively charged, this is positive charge, that left. And what happened? This positive and this negative ions come close to the junction like this. This process continues and you are able to get the positive charge on the right side of your junction and negative charge on your left side of the junction. Now see, this is like polarization. I can say that polarization, and that is just like in the simple way there is some capacitance, or in other very simple way we can see there is a resistance and there is a resistance of development. It means एक ऐसा रीजन मेरे पास बन जाएगा जिसमें वन साइड जो क्या है आपके पास पॉजिटिव चार्ज आ गए और एक साइड आपके पास नेगेटिव साइड चार्जेस आ गए. नाउ सी so this region is created automatically after the movement of the charges from one side to other. If I see this, then what is there? If we can say that there is development of internal field. Yes, field है आपके पास field. If this I say EI, this always for positive to negative like this, if plus q to minus q. So there is development of electric field that takes place in this process. Now if there is some distance is there, I can say that there is also development. This is plus. There is also development of potential difference that is set up in this side. That is positive potential is there, negative potential is there. So along with EI there is induction of barrier potential is there, that is abbreviated as VV at the same time. So this barrier potential is the is the potential that is set up according to the electric field that is set up along with the junction sides. Okay, so this is the first case. This is the first case. This is also known as stopping potential. Is the stopping potential, क्योंकि जैसे ये सेटअप हो जाएगा, अब what happen? There is it restrict the movement of majority charge carrier to the other side. It stops. This is the basic common PN junction that we have developed in the previous lecture, right? Now next step, because I want the in PN junction, this is very limited use. Otherwise, because I want that there should be a continuous flow of current or charge inside the PN junction diode, right? So I want to continuous flow of current. I want a continuous change in the voltages. And one more thing, this particular region aside to your barrier potential, this particular region is known as depletion layer. Depletion layer. This is known as depletion layer, and the width of depletion layer is 10 minus 6 meter, that is 1 micrometer be the width of this. It may vary, it may vary from 10 minus 9 meter to 10 is to minus 6, right? Okay, so depletion layer भी आप लोगों ने देख लिया कि how that is created, right? This is in the next step now. Now I want that my PN junction diode in that particular situation, there should be no restriction on the flow of the charges. So what I have to do? What I have to do? I have to do two steps. Two steps. I have to do for that is two steps I have to take. What steps? This is your P type and N type. Okay, I want to go to the now on PPTs. So this is the very first step that I want to do here. Here what did this is P type, this is N type. You just this is your negative terminal. This section is positive. This is the positive. Then you P this P section. Then you this is the P section of battery. You just add a battery there. This is the battery. You just add the battery there, and positive terminal of the battery that is connected to the positive of the that is P section, and this is negative, so this is the negative charge is there. So negative of this that connected to the negative of the battery. This is negative of the battery, this is positive of the battery. You just put a battery here, positive and negative, like this. So positive connected to this side, negative connected to this side. Okay. And what the use of microampere? This is the emitter that is used in series. You know this series, right? If you want to, in practical way, you have to add. You have to make this type of diagram for that. Okay, that's not the issue here, but what P type of the battery that is connected to P section of the PN junction diode, N type of the battery that is connected to the N section of PN junction diode. Then there is development of forward biased PN junction. Forward biased PN junction, right? So this is your first type, that you just modify your ordinary PN junction diode to forward biased PN junction diode. Okay. So one more thing, that what are the symbols that are used in this situation? This situation that I just made. Okay, so this is the very first step. You just if I yes, I know the symbol for diode. This is the symbol for diode, right? This is your P section of the diode, this is your N section of the diode. Symbolically we can represent this, and in few books we can represent like this. This is the representation of a diode. Diode representation. Diode representation. Now, okay, so you can represent your PN junction diode in forward bias like this. So this is your diode, PN junction diode. This is plus, this is minus, and then you plus of the battery, that is long line, and if this is long line, then this is short line. This is the negative of the battery, and you can connect both two. And yes, I am saying the battery, it may be a variable voltage you are applying now. This is the variable voltage. Okay, so yes, then this is milliampere, and that is ammeter that is also connected to this, and the current from positive to negative. So the direction is like this. Your current, this is the forward bias current. I represent this IF like this, right? And now we have the two types of voltages. This is your VF, forward voltage. This is the forward current is there, and there is another voltage is there due to the diode personal. that is VV. And if your forward voltage you are applying more than barrier like this, barrier voltage, then there is a flow of current. Yes, it's also important. Barrier voltage for silicon, if you are using the material silicon, then it is 0.7 volt. Yes, in the next point I explain this. And barrier voltage, if you have the germanium as the material, then it is 0.3 volt. Okay, what the meaning? If I want to see the BI characteristics, then if I take the, suppose that germanium, then up to 0.3 volt, this is your forward voltage. I am representing this, right? So up to 0.3 like this is behave like a normal normal PN junction diode, that is also non-ohmic, and after that it starts working like this. This is the BI characteristics for forward biased. Okay, so how the current flow in the forward biasing case, that's we have to see. That's we have to see. Okay. Okay. Forward biased PN junction diode case of this. So you just have a scenario like this. I can show that from this diagram too. Yes, right. Okay, I take this this figure. Okay, I can take this figure. Okay, now what happened in forward biasing? These are the majority carriers in P type. These are the minority carriers. Majority carrier in this is the minority carrier. And what happened? This is the plus, that is the positive force. This is also positive force. Then what happened? ये भी positive है, ये भी positive है, ये भी positive है. Obviously there is a repulsion, and automatically if this is the starting width of your depletion, then it start decreasing. It start decreasing the width of the depletion layer, that decreases in forward biasing. If depletion region width decreases, then resistance also decreases. If resistance decreases, then there is increase in the current flow like this. Okay, right? This is the, yes. So this can be understood by this. In this case, yes, this is P type. This is the potential hill. If these are the holes, these are the holes, and after doping, their energy level is, yes, यहाँ energy level होना था, doping के साथ the energy level is this, increases, and in N type the same is the case. And then this is the energy Venn diagram for this case. If holes have to move, then they have to cross this potential hill, then that reach to the N type, and electrons have to cross this potential hill, then they can reach to the this. Okay, ठीक है. So during the forward biasing, the height of the potential hill is reduced. हाइट इसलिए रिड्यूस हो गया क्योंकि आपका जो डिप्लेशन विड्थ है लेयर का, वो भी क्या हो गया है, डिक्रीज हो गया है, वो भी डिक्रीज हो गया है, राइट. एंड अगर वो रेजिस्टेंस कम हो गया तो देर इज अ फ्लो ऑफ करंट and the current start from positive terminal and it reach to the negative terminal. We can measure by making use of ammeter there, right? And this is variable voltage, and I am representing that VF, and their variable potential, that is VV, along with the, this is because there is, this is P side, then there is immobile charges are there like this, and the potential is barrier potential, and barrier potential, that depends upon the which type of material you are using for making the forward bias PN junction diode. Okay, so this is your forward bias case, and similarly then we can also make the second type reverse biased. Step 2, if I connect the P section of your PN junction to the negative of the battery, this is positive, this is negative of the battery, or then what happened? Now all these are positive charges, their direction of movement, पहले डायरेक्शन कहाँ थी, ऐसे थी, इनकी ऐसे थी, अब अभी तुम्हारा उल्टा हो गया, अब आपकी डायरेक्शन कहाँ चली जाएगी इनकी, लाइक दिस. इलेक्ट्रॉन्स की कहाँ चली जाएगी, बिकॉज ये पॉजिटिव है, ये आपके पास नेगेटिव है, तो इलेक्ट्रॉन्स की डायरेक्शन कहाँ चली जाएगी, इलेक्ट्रॉन यहाँ मूव करेंगे, इलेक्ट्रॉन यहाँ मूव करेंगे, लाइक दिस. करंट वहाँ मूव करेगा, ये सब जानते हैं, बिकॉज इलेक्ट्रॉन का जो फ्लो होता है वो करंट से अपोजिट होता है. भी ऑल ड्रिफ्ट ऑफ इलेक्ट्रॉन्स है, ये आपके छोटे बेसिक कंसेप्ट है +1 +2 के, यू ऑल नो दिस. सो आपके जो मेजॉरिटी कैरियर इन एन सेक्शन है वो कहाँ जा रहे थे, आपके पॉजिटिव टर्मिनल, और जो आपके होल्स थे जो कि पॉजिटिवली चार्ज है वो जा रहे हैं नेगेटिव. अब आपके करंट का जो फ्लो है उल्टा हो गया, दिस इज फ्रॉम पॉजिटिव टू नेगेटिव. So this is your reverse current. This is your direction of the current. The current direction is from this to this point. And वहाँ हम इसमें फॉरवर्ड बाइस में हम मिली का यूज़ कर रहे थे, बिकॉज आपके इलेक्ट्रॉन यहाँ जाके चले गए, यहाँ से आपके इलेक्ट्रॉन जा रहे हैं. अब बात ये है कि जब इलेक्ट्रॉन चले गए तो करंट कैसे होगा. यस, एक one point that is also be discussed in forward biasing. Kindly note that point. Now, yes, अब ये यहाँ से जाकर के इस इलेक्ट्रॉन के साथ मिल जा रहा है. फॉरवर्ड बाइसिंग में तो इजी हो गया, डिप्लेशन लेयर कम है, ये क्या हो गई, जाकर के रिकम्बाइन हो गए, ये रिकम्बाइन हो गए. Then how the current is there? This is a question. How the current is there? Yes. आपने बोला है आपकी इंटरनल फील्ड क्या थी, यहाँ से डायरेक्शन थी उसकी, EI की डायरेक्शन यहाँ थी डिप्लेशन लेयर के अंदर. एक्सटर्नल फील्ड की डायरेक्शन क्या है आपकी, जो इलेक्ट्रिक फील्ड इसमें है, पॉजिटिव टू नेगेटिव, दिस इज द एक्सटर्नल फील्ड. EI ये डिप्लेशन लेयर की बात कर रहा हूँ मैं. ओके, वेयर इज द करंट, इलेक्ट्रॉन ये तो रिकम्बाइन हो गए क्या हो गए. फॉर एग्जांपल, दैट इज, अगर मेरे पास एक पॉजिटिव है एक नेगेटिव है तो रिकम्बाइन हो गया, मेरे को गामा मिल जाएगा, ख़त्म हो गए, ये तो चार्ज कैरियर में टेक पार्ट नहीं करते, तो फिर करंट कैसे आ गया. काइंडली नोट इट, जैसे ही एक रिकम्बिनेशन होगा वैसे ही आपके जो लैटिस है जिसमें सिलिकॉन के साथ बॉन्ड है, दिस इज़ योर कोवालेंट बॉन्ड, ये जैसे एक रिकम्बिनेशन हुआ एक बॉन्ड टूट जाएगा, और एक बॉन्ड टूट जाएगा तो एक आपको क्या मिल जाएगा, एक पॉजिटिव चार्ज कैरियर मिल जाएगा, एक नेगेटिव चार्ज कैरियर मिल जाएगा, यानी इलेक्ट्रॉन मिल जाएगा. ये इलेक्ट्रॉन उस रिकम्बिनेशन के रिप्लेसमेंट में आपको किसने क्रिएट करके दिया, बैटरी ने क्रिएट करके दिया. बिकॉज ये जो लैटिस है किसका है, सिलिकॉन का है या जर्मेनियम का है, SI का है, जर्मेनियम का है। SI के साथ बॉन्ड है कोवलेंट में, जर्मेनियम के साथ बॉन्ड है। अब जैसे रिकम्बिनेशन होता है तो जैसे एक रिकम्बिनेशन होगा, यहाँ से ये क्या क्या कर देगा, एक कोवलेंट बॉन्ड तोड़ देगा, और जिससे एक पॉजिटिव और नेगेटिव यानी इलेक्ट्रॉन आपको मिलता रहेगा, होल्स आपको मिलते रहेंगे, पॉजिटिव चार्ज कैरियर। और आपके आपके जो होल्स हैं वो उसी डायरेक्शन में कहाँ जाएंगे, पॉजिटिव से नेगेटिव डायरेक्शन में जाएंगे होल्स, और जो दूसरा इलेक्ट्रॉन है वो ऐसे चलता रहेगा। और करंट का फ्लो आप देख रहे हैं, दिस इज द फॉरवर्ड करंट। यस, दिस इज वेरी वेरी इंपॉर्टेंट टू से। ये जो एक्चुअली आपके पूरे क्रिस्टल के ऊपर जो फील्ड है दैट इज योर EI, है ना, या मैं इसको बोल सकता हूँ, ये तो आपके पास क्या था, ये आपके पास वोल्टेज, अप्लाइड वोल्टेज, ये BF बोला गया। जैसे आप वोल्टेज बढ़ा रहे हैं वो बॉन्ड टूटना शुरू हो जाएंगे, बॉन्ड टूटना शुरू हो जाएंगे, आपको इलेक्ट्रॉन मिलना शुरू हो जाएंगे, और एक कम्बिनेशन चलता रहेगा, यानी आपका फ्लो चलता रहेगा, जैसे पानी हिलता रहेगा और किश्ती चलती जाएगी, लाइक दिस। सो दिस इज द वर्किंग ऑफ योर फॉरवर्ड बायस्ड PN जंक्शन डायोड। इसी तरह से रिवर्स में, रिवर्स में अब उल्टा हो गया है। चलिए मैं अगली फिगर लेता हूँ। रिवर्स में क्या हो गया आपके पास, एक तो ये आपके पास कहाँ गया, दिस इज, चलिए मैं इसी को लेता हूँ। ये रिवर्स में उल्टा क्या हो गया है, एक तो जो आपके होल्स हैं उनकी डायरेक्शन कहाँ चली जा रही है, लाइक दिस। इलेक्ट्रॉन जो माइनॉरिटी कैरियर है उनकी डायरेक्शन भी बड़े काम करेगी। यहाँ माइनॉरिटी कैरियर की डायरेक्शन कहाँ है, ये क्या है क्या, ये इलेक्ट्रॉन है, तो इलेक्ट्रॉन तो कहाँ जाएगा, पॉजिटिव की तरफ जाएगा, बैटरी के इलेक्ट्रॉन तो पॉजिटिव की तरफ जाएगा, ये पॉजिटिव है बैटरी का इलेक्ट्रॉन, तो यहाँ माइनॉरिटी कैरियर यहाँ जा रहा है, लेकिन मेजॉरिटी कैरियर तो जा रहे हैं, मेजॉरिटी कैरियर सीधा बैटरी के पास जा रहे हैं। यहाँ वाले कहाँ जा रहे हैं, ये भी है, इनकी डायरेक्शन भी उल्टी हो गई है, ये भी बैटरी की तरफ चले जाएंगे। मेजॉरिटी कैरियर तो चले गए सभी, बोलने का अर्थ क्या है, मेजॉरिटी कैरियर तो बैटरी की तरफ चले गए, लेकिन ये माइनॉरिटी है, ये कौन सा है, पॉजिटिव चार्ज है, तो ये तो नेगेटिव कर जाएगा, तो इसकी डायरेक्शन तो यहाँ रहेगी, इसकी डायरेक्शन, इनकी डायरेक्शन यहाँ रहेगी, और जो आपके ये इलेक्ट्रॉन्स हैं माइनॉरिटी में, यानी करंट किसके थ्रू रहेगा, करंट रहेगा माइनॉरिटी कैरियर्स। सो माइनॉरिटी कैरियर्स जो है, these are the basic developer of current in reverse biased PN junction। और जो ये करंट प्रोड्यूस करते हैं उसको आप रिवर्स करंट, लीकेज करंट या सैचुरेशन करंट भी बोलते हैं। यस, लीकेज करंट, मैं आई एम राइटिंग दैट IR, सैचुरेशन करंट, ओके, इन दोनों में अंतर है। IS, this IS saturation current, this current is only due to minority, और इस करंट को कई बार क्या इसको और लीकेज करंट, इसको लीकेज करंट। एक क्वेश्चन था कि ज़्यादातर हम सिलिकॉन प्रोड्यूस करते हैं ना कि जर्मेनियम। जर्मेनियम की बाकी सभी प्रॉपर्टी जो है सिलिकॉन से बेटर है, जर्मेनियम की सभी प्रॉपर्टी सिलिकॉन है, लेकिन एक प्रॉपर्टी है जो कि इसको जर्मेनियम से बेस्ट बना देती है। आई हैव मेड अ टेबल एनीवेयर, आई वांट टू शो दैट। यस, दिस इज, काइंडली नोट इट, देखिए जरा, क्योंकि लीकेज करंट का कंसेप्ट है तो ये बहुत इंपॉर्टेंट है मेरे लिए आप लोगों को बताना। ये देखिए जरा, यहाँ मोबिलिटी ऑफ इलेक्ट्रॉन इन जर्मेनियम 0.39 मीटर स्क्वायर पर वोल्ट, इन सिलिकॉन इट इज 0.135, कम है। इलेक्ट्रॉन की मोबिलिटी सिलिकॉन में कम है, जर्मेनियम में ज़्यादा है। एंड सेकेंड पॉइंट, मोबिलिटी ऑफ होल्स 0.19 मीटर स्क्वायर पर वोल्ट सेकेंड, दैट इज इन जर्मेनियम, but it is 0.048 meter square per volt second, that is in silicon। इंट्रिंसिक कंसंट्रेशन, प्योर की बात हो रही है, प्योर जर्मेनियम, इसका इसमें नंबर ऑफ चार्ज कैरियर कितने हैं, 2.5 10 19 पर मीटर क्यूब, और इसमें सिलिकॉन में 1.5 इंटू 10⁻16 मीटर पर मीटर क्यूब. नाउ सी, everything in every sense, germanium is much better than silicon. Germanium is much better than silicon, but in all over world for application purposes only silicon is preferred over the germanium. The reason is, yes, energy band, one more property, energy band इसका कम है 0.78, इसका ज़्यादा है, एनर्जी बैंड कम होगा, मैक्सिमम जो सेमीकंडक्टर बिहेवियर सबसे ज़्यादा किसका होगा, इसका बैंड गैप तो बहुत ज़्यादा है. लाइक दिस, इन एवरी सेंस germanium is much better than silicon, but why it is not preferred? The reason is leakage current. The leakage current of silicon is less than that of the germanium. This is the main cause that the people, the scientists, the engineers, they are working on silicon rather than germanium. Kindly, this is very very important. And okay, again I want to go my topic. Then yes, here we are in forward biasing, reverse biasing, and where is this is the case. Okay, so हम लोगों ने ये तो सब अंडरस्टैंड कर लिया कि कैसे कैसे अब माइनॉरिटी जो है ये पॉजिटिव है, ये नेगेटिव है, मेजॉरिटी तो चले गए, मेजॉरिटी दोनों साइड के चले गए, अब बचे आपके पास माइनॉरिटी. दिस इज पॉजिटिव, दिस इज नेगेटिव. ये नेगेटिव कहाँ जाएगा, यहाँ की तरफ आने की कोशिश करेगा, ये पॉजिटिव है, ये यहाँ की तरफ आने की कोशिश करेगा. तो यहाँ से इनकी मूवमेंट से जो करंट प्रोड्यूस होगा उसे बोलते हैं हम रिवर्स सैचुरेशन करंट, और सैचुरेशन करंट और लीकेज करंट. अब ये जो है आपने जो करंट प्रोड्यूस किया है बहुत कम, इन माइक्रोमीटर यू आर लुकिंग एट दैट, राइट. व्हाट हैपन, अब इस नेक्स्ट स्टेप में ऐसा क्या हो जाता है कि आपका जो रिवर्स करंट है वो बहुत ज़्यादा बढ़ जाता है. हम कैसे इसको स्टडी करेंगे, हम कैसे इसको समझेंगे, ओके. क्योंकि यहाँ जो आपकी इलेक्ट्रिक फील्ड है, इलेक्ट्रिक फील्ड कहाँ से कहाँ तक डायरेक्शन थी, ये पॉजिटिव वाले थे, ये इसकी बात करिए जरा आप. ओके, मैं आई वांट टू गो इन द नेक्स्ट पिक्चर दैट यू हैव डिप्लेशन लेयर हेयर. दिस इज प्लस प्लस, दिस इज माइनस माइनस माइनस. Electric field is this, internal electric field is this direction, your barrier potential also in this direction, and yes, now see this potential and this potential, they support each other. It means your electric field की डायरेक्शन है दैट इज आल्सो सपोर्टेड, एंड द रोल ऑफ इलेक्ट्रिक फील्ड इज वेरी वेरी मच इन दिस केस. नाउ द इलेक्ट्रिक फील्ड, collective electric field and collective voltage of the system that breaks the silicon covalent bond or germanium covalent bond, but in very intensive way. So if you see the BI characteristics, I will show in the next step. Yes, this is, yes, you are observing that for forward biasing it is a simple PN or junction like the workings like this. But in reverse case, yes, this is the point of leakage current. The current start, that is this portion is your leakage current. Then After that, there is a breaking of the silicon covalent bond starts, and it starts very intensively because your BV, that is supported your VR, and electric field E, that's for your actual electric field. So situation is very very strong, that there is obviously breaking of the bonds that takes place. And here you see, when there is breaking of bond starts intensively, the voltage, the current, the free electrons, the leakage current, that is, it sharply increases to maximum value. And this portion, I can say, this is the avalanche current is produced here. Avalanche current is produced here. Avalanche current is produced here, and correspondingly, yes, if I see this, the voltage of the system, that increased very much. This is the reverse voltage, and you know that इसी वोल्टेज के सहारे हमने एक जीनर डायोड बनाया है, that is जीनर वोल्टेज, that is breakdown voltage in reversed PN junction. आगे हम देखेंगे इसको जीनर वोल्टेज. Both are quite different, but we can understand that high voltage is developed across the system, and sharp peak will be in the VI characteristics. This is the functioning of your reversed bias PN junction as well as forward bias junction. This figure, kindly note this figure. This is your VI characteristics. This is your VI characteristics of PN junction, like this. This is the forward voltage. In few weeks, that can be VF, and this side, this voltage is VR. This is the leakage current, or I can say this is the reverse current, and direction the current is your forward current, and this is the scenario. And yes, one more thing, in reverse we have to use the micro ammeter during your experiment, and during forward biasing we have to use the milliampere ammeter reading. Kindly note this. So there is a avalanche breakdown takes place due to this concept. Okay. So now I should stop this, and kindly up to this point, this topic will be clear to you, or if it is not clear, then again kindly ask to me. If you have any query, you can ask in my class. ठीक है, thank you very much for the day. Thanks a lot. Thanks a lot. Query, any query you can note on your copies, then come to class, we will discuss there. Thank you very much.